lesson of organic chemistry, we will be looking at two organic families called alkenes, hear that E-N-E ending, and the alkynes, hear the Y-N-E ending. Alkenes and alkynes are the focus of chapter 12. Alkenes are unsaturated hydrocarbons that contain one or more carbon-to-carbon double bonds. The alkynes are unsaturated hydrocarbons that contain triple bonds. Alkenes contain double bonds. Alkynes contain triple bonds. The simplest of the alkenes would be a single carbon-to-carbon double bond. Thinking about what that structure looks like, C, double bond C, and the hydrogens coming off is the simplest, of course, there is no one carbon as we had in the ANE family alkanes known as methane. So the simplest alkene would be known as ethylene. However, that is a common name. We'll soon learn its IUPAC name, ETHENE, showing this ending, the suffix ENE, showing us that it indeed has a double bond. Acetylene, which is a fuel used often in blowtorches, is the simplest of the alkyne family. Notice it is a C, triple bond C, a very linear molecule. Acetylene is the common name for the IUPAC name ethine, ETHYNE, the simplest of the alkyne family. Alkenes contain double bonds. Alkynes contain triple bonds. Thermal cracking is a process in which a saturated hydrocarbon is converted to an unsaturated hydrocarbon, releasing molecular hydrogen. To model that, we could take a structure known as ethane, a saturated hydrocarbon. Saturated, we learned in our last chapter, has all single bonds. Molecular formula here, C2H6. In the process of thermal cracking, which is very intense heat, 800 to 900 degrees Celsius, we start to see a release of molecular hydrogen. Cracking is to break bonds. And if I remove a hydrogen from each of the carbons, we could see the formation of the double bond between the two carbons. Remember, carbons each need to have 4 bonds, and molecular hydrogen, where these H's, they're going to come together to form the single bond molecular hydrogen, as we see here. Thermal cracking of ethane produces ethene, the simplest of the alkenes, but keep in mind, ethylene is its common name, and it's probably more common to hear this is unusual, more common to hear the common name than the correct IUPAC name. There we go. So the common name for the very small hydrocarbons in these doubles and triple bonds generally still are what we hear in the world of chemistry. And then, of course, the molecular hydrogen is released to keep the equation balanced. The alkene structure, according to our valence shell electron pair repulsion theory, the Vesper theory, predicts bond angles of 120 degrees about each carbon. Now think about that in terms of hybridization. This particular carbon right here has 1, 2, 3 electron domains. So its hybridization we know to be sp2, representing what's called a trigonal planar geometry. And in a trigonal planar, an equilateral triangle is created where all bond angles are exactly 120 degrees. An equilateral triangle, every angle is the same of 120. What we're noticing here is just a little bit difference of observed versus the predicted, but close enough to think of an equilateral triangle giving you the bond angles close to 120. What we do notice, though, is that if we start to create a longer carbon chain where we have a little bit of crowding up here, for instance, we have a methyl group hanging off of this carbyl chain. And again, the IUPAC name here is propene. 1, 2, 3 carbons in the chain. So prop is our prefix for 3. Propene, here that ENE ending lets us know there's a double bond. But because of the crowding here, you're going to see this particular bond angle actually increase from predicted 120 up to about 124, 125 if you round a little bit, just to kind of ease that crowding. And then, of course, this particular bond angle would be a little less than 120. So the more substituents you get on the alkene chain, you'll start to see a bend in that predicted bond angle to be greater than 120, just to alleviate the repulsion. And again, that's the repulsion theory up here according to Vesper. We want to create bond angles that alleviate as much crowding as we possibly can, and it will do so by making bond angles greater than the predicted 120 from the trigonal planar sp2 hybridization. If you look at the molecular model of ethylene, ethylene is common name for ethene, C2H4. And if you actually could take the time to build this, if you have your molecular models, you would see that the 2 carbons of the double bond and all 4 hydrogens all lie within the same plane. It's a very flat molecule. Nobody's hanging up or sticking out, if you will, in terms of the 3-dimensional analysis. And we have mentioned that it's sp2 hybridization, and its geometry would be trigonal planar about each of those carbon atoms. Because of the double bond here, remember that one is considered pi and the other is considered a sigma, kind of again back to the inorganic. I'll make those better. 1 sigma and 1 pi bond, and that's just simply the orientation. There is no rotation allowed in a double or triple bond, which is different than a single bond. Now, if you have your models and you were to build a saturated hydrocarbon, saturated means all our single bonds all contain enough hydrogens to fill the octet rule, you can twist and turn and rotate those bond angles around those carbons. But if you were to eliminate the hydrogens and go back to create a double bond as we have in the ethene, this double bond here makes this molecule very rigid and will not twist or turn. So it really is a very predictable bond angle, more so really than the infinite number of bond angles possible in a rotational curve or in a saturated hydrocarbon. Last chapter, we also talked about cis and trans isomerism. Cis, if the substituent branches are coming off in the same direction, or trans if they are coming off in the opposite direction. Because because of this double bond being very rigid, what we're looking at in this butene, the butene, here the ENE for 4-carbon chain, is showing a cis transformation. If indeed off of the double bond, we see the bond angle on the same side. I'm just counting. I really think that this is an error in it certainly is. This particular structure does not match what's in your book, and I was just looking at it, there's only 3 carbons. So let's draw that better. CH3C, C double bond C, and then down here needs to be that 4th carbon, and here are the other 2 hydrogens. This is the correct structure for cis-2-butene, ENE, not the one that's on this slide. Now take a look, they've drawn this correctly. We have 1, 2, 3, 4 carbons for the butene name, but now they're in opposite sides of that double bond. This is correctly named trans 2-butene. The number 2 is telling us the location there of the double bond. We could have indeed this structure for butene as well. So we're just letting you know where the double bond is located in the chain. When I see 2, let's see here, 2-butene, see this number 2? It's letting us know that the origin of the double bond starts at carbon 2, so it's between carbon 2 and 3. If I hear this called 1-butene, I would know that the double bond originates at carbon 1 and ends at carbon 2. So that's really just letting us know where in the chain the double bond is located. But to repeat the lesson of this slide, same sides would be cis, opposite sides of the double bond are known as trans in terms of the geometry of the molecule. In our third section of our chapter, we're asked to name alkenes and alkynes. Alkenes and alkynes are named using the IUPAC system of nomenclature. And as we'll see, some of them are still referred to as their common names, especially the smaller hydrocarbons. The key to naming IUPAC for alkenes is the ending ENE. Just as we learned in our last chapter, ANE tells us that all the carbon-to-carbon bonds are single bonds, that they are saturated. ENE tells us that there is a carbon-to-carbon double bond somewhere in the carbon chain. Now the rules for naming them are as follows. Number 1, find the longest chain that includes the double bond. Very important that when we're numbering, the double bond must be included in that long parent chain. I don't care if you can find a longer chain somewhere in the molecule, there must be a parent chain with a double bond. Number 2, number the chain from the end that gives the lower set of numbers to the carbon atoms in the double bond. The double bond gets priority, not the substituent groups. The lowest number is given to start from the side of the parent chain that gives the lowest number to the carbon-carbon double bond. Rule 3, locate the carbon-to-carbon double bond by the number of its first carbon. That will become part of its name. Branched alkenes are named in the same manner as alkanes, where substituent groups are located and named. And if there's multiple substituent groups, we name them in alphabetical order. Let's take a look at an example. Here we have a straight chain, and I know when I say straight chain, it just means that there's no branches, that these are tetrahedral 109.5 is why we start seeing them in terms of this geometric pattern. But we have 1, 2, 3, 4, 5, 6 carbons in a row, and the rule will tell us make sure that you start numbering from the side that gives priority to the smallest number of the double chain. It is not okay to number that in this order. We would not name this 5-hexene because 1, numbering right to left, gives the double bond the lowest number possible. Again, here I would number from right to left, not left to right, because now I'm giving priority to this double bond. There are 6 carbons in this chain. Carbon 1 and 2, between carbon 1 and 2 is the location of our double bond. So you can see in the name, 1-hexene is telling you the location. And at carbon 4, we have a methyl group, a 1-carbon branched substituent group. 4-methyl 1-hexene. Notice here, I must count the parent chain in terms of locating the double bond. I definitely could find longer branches, 1, 2, 3, 4, 5, 6, I could find a longer chain, but if I were to number that way, I don't include the double bond. So that's not how we do it. We must include the double bond when we're naming. And I would give priority to the lowest number. Carbon 1 and carbon 2 is the location of the double bond. So I can see in this parent chain that contains the double bond. And keep in mind, it wouldn't matter if we went 1, 2, 3, 4, 5. We'd end up with the same name. It's at carbon 3 that there is a 2-carbon branch called ethyl. But we also have a 2-carbon branch at carbon number 2. So at carbon 2, we have an ethyl branch. And at carbon 3, we have an ethyl branch. 2 carbons. So we would name that 2, 3, diethyl 1-pentene. The location of the double bond is between carbon 1 and 2, 1-pentene. And at carbon 2 and carbon 3, we have a branch of an ethyl, a 2-carbon branch, each at carbon 2 and 3. So many similarities when we name triple bond compounds known as alkynes. We follow the same rules, but now our ending means Y-N-E, showing the presence of a triple bond. A little bit different structure here. Notice that we have 1 bond below and 1 bond above the original carbon chain, showing a triple bond. Give priority to the location of the triple bond. We have 1, 2, carbon 1, 2, 3. See how that's very linear. That's very difficult to actually spot with the beginning chemistry student. At the end of the triple bond is a carbon, but because that triple bond just flattens that geometry to be exactly 180, don't forget that there really is a carbon right here. So 1, 2, 3, either up or down there, gives us 4. So between carbon 1 and 2, there's a triple bond, 1-butyne. And at carbon 3, we have a substituent branch. So we would name it 3-methyl 1-butyne. Notice again here where you see the origin of a triple bond, a very flat molecular geometry. That triple bond, if you were to build one using your molecular models, completely makes that line, just that linear 180-degree, very flat region of the molecule. So when you're counting for triple bonds, be sure to note that you're not going to have a bend. And we're so used to seeing that in alkanes and alkenes that it bends every time we have a carbon, but not the case for a Y-N-E triple bond. Carbon 1, 2, 3, 4, 5, 6, and either straight down, to the left, or to the right gets us carbon 7. So at carbon 6, we have 1 kind of coming this way to give us the 7th branch, heptyne. And then here's a branch of a methyl, another branch of a methyl. So 6,6-dimethyl between carbon 3 and 4, 3-heptyne. I have my book open to find some examples to page 356, if that's of help for you to see the structure I'm going to try to draw. We're going to draw some hydrocarbons. These are unsaturated hydrocarbons and try to name them. So let me draw what I see first. We have CH2, CH, parentheses, CH2 taken 5 times, CH3. Now let's try to get an idea of what this looks like. My first carbon has 2 hydrogens on it. My next carbon has 1 hydrogen on it. Then I see a series of CH2 taken 5 times. So here's 1, 2, 3, 4, 5, and then the terminal carbon with 3 hydrogens. Now you notice right away that I have an area right here that is not meeting the octet rule, where each carbon must have 4 bonds. So that's telling me that there must be, I have 1, 2, 3, and 1, 2 so far. So what if I were to draw right here a double bond? Now I meet the criteria of the octet rule, where each carbon now has the 8 valence electrons with the 4 bonds it needs. So when I see this structure right here, that's telling me I don't have enough carbons to be saturated. That's the unsaturated region. It must contain a double bond. Or if it had just CH, C, then I know it would be a triple bond. So let's go ahead and name this. How many carbons in our chain? 1, 2, 3, 4, 5, 6, 7, 8. At carbon number 1, we have a 8 carbon chain, 1 octene, ENE. Let's draw a next structure. Again, I'm just pulling the letter H3C. This is letter B example. C double bond C, CH3, CH3, and an H. Name that compound. I'll try to make that bigger. And even if I slide down, that might give us a little more room to see. There we go. CH3 coming off of this carbon here. Well, first of all, I need to find the longest carbon chain that contains the double bond. Now I can go 1, 2, 3, 4, 1, 2, 3, 4, and that's okay. But when we number, well, it doesn't matter. So let's go 1, 2, 3, 4. So here's what I see. At carbon 2, there's a double bond, and the length of the chain says, here's my root word, 2-butene. What I also know is at carbon 2, there is a methyl group. And again, depending on how I number, it could have been up or down. But here at carbon 2, there is this methyl group. And what I'm referring to is right here. This now is considered a substituent group. So at carbon 2, the substituent group is methyl. 2-methyl, 2-butene. Shall we try another? I'll draw the structure provided in letter C. CH3, parentheses, CH2, taken twice, C, triple bond C, CH3. First carbon is the terminal carbon with 3 hydrogens. I have 2 carbons in a row, each with 2 hydrogens. Then I have a carbon triple bond and a terminal carbon. Number from the side that gives the lowest possible number to the carbons involved in that triple bond. There are 6 carbons in my chain, and between carbon 2 and 3 is the triple bond, so here's what we have. 2-hex, Y-N-E, 2-hexyne. For Y-N-E, hexyne. No substituents, it's just a, no branching here, so just plain old 2-hexyne. Let's try another. And again, I'm going down now to problem 12.1. And now these are stick formulas, so let me try my best. 1, 2, 3, 4. There's a double bond. And at this point, I see 2 branches. Name that structure. That's all right for trying to draw. So again, priority is given to the lowest number that contains the double bond. If I went down, I'd end at 4. So the longest chain I'm finding that contains the double bond is between carbon 1 and 2 in a 5-carbon chain. So here's what I know so far. I have 1 pentene, a double bond ending, ENE, of a 5-carbon chain. Something's going on here at carbon 3. I have 2 substituent branches, both of 1 carbon. So I have 2, 2 dimethyl, 1 pentene. Why did I write 2's when I counted 3? Let me repair that. Sorry, that's a mistake. 3,3-dimethyl 1-pentene. Clearly at carbon 3. Shall we try another? Here I have 1, 2, 3 coming off here. Name that structure. These are fun to draw if you're drawing with me. So let's find the longest carbon chain that contains the double bond. 1, 2, 3, 4. 1, 2, 3, 4. Lots of possibilities there. Between carbon 2 and 3, I have a double bond. So here's what we have so far. In a four carbon chain, between carbon 2 and 3, there's a double bond. That tells me to name it 2-butene. However, at carbon 2 and at carbon 3, we have a substituent group, a methyl. 2,3-dimethyl 2-butene. One more. Let's try a triple. Now this is an interesting structure. Let me try to draw this. I've got a straight line. About here and here I have one coming off of each direction. Then I have a structure like this. Name that molecule. I might have drawn this area too long, but that's okay. Well, let me make that better because it is misleading. It's very, very much too long. It should look more like this. Alrighty. So again, here we have a structure where I'm seeing a triple bond. Remember that triple bond makes the molecule so flat. This is carbon 1. Here is carbon 2 at the end of the triple bond. Here is carbon 3, and I could go up, down, or straight ahead. It wouldn't matter. We're going to end up counting to carbon 4. 4 carbons in that structure. So at carbon number 1, there is a triple bond in a 4-chain member, 1-butyne. And at carbon number 3, I have 2 branches, each considered a methyl group. So I have 3, 3-dimethyl 1-butyne. Good fun. As I mentioned earlier, many of these compounds contain common names, especially the lower molecular weight, the small chain carbons. We should become familiar with the common names simply because we hear them more often in the chemistry world than the IUPAC. 1-to-1 carbon, the simplest of all alkenes, commonly called ethylene. 3 carbons has an IUPAC of propene. Notice these do not need numbers. There's no other choice of where the double bond could be. Propene, commonly called propylene. And here, the iso group is the common part here. 4 carbons, so isobutylene. However, the IUPAC would actually name this carbon as a substituent. 2-methylpropene has a common name of isobutylene. Ethyne is called acetylene, blowtorch gas. This one is probably the most misleading because it still ends in an ENE, but it's a triple bond. Very unusual. You can see the common name not matching the IUPAC name. Propyne is called methylacetylene, has a methyl group on the acetylene chain. And here we have 2-butyne, which they commonly call dimethylacetylene. So again, the common name of the INE comes from this guy, the root word of acetylene. Other than those common names, you will not be held accountable for any others. Practicing cis and trans geometric configurations of alkenes, when we consider the orientation of carbon atoms as the parent chain and determine whether it is cis or trans. For instance, what might trans 3-hexene look like? Well, let's just get our bearings and kind of figure out what we're being asked to draw. 1, 2, 3, 4, 5, 6 carbons in a row, where between carbon 3, the origin, and carbon 4, there is a double bond. creating an area of rigidity where it will not be, the bond is not able to rotate. So I'm going to start with the backbone of carbon 3 and 4. And what I mean by that, kind of beginning with this particular area of the molecule. Now because it says it's trans, that reminds me that trans are on opposite sides. The geometry of this molecule would say the next two carbons come up, whereas these two carbons must point down. It would be highly recommended to build that with your molecular geometry kit and show yourself how this truly creates a linear area of the molecule that you're not able to just rotate between cis and trans. We cannot rotate. That a completely different molecule, even though it didn't ask me to draw, the cis structure has completely different physical properties, completely different chemical properties than the trans molecule. They're not able to just flip back and forth, as we did see in the last chapter of our saturated alkanes, where we could have bond rotations. Let's try another. What does cis 3,4-dimethyl 2-pentene look like? Well, I still have to go 1, 2, 3, 4, 1, 2, 3, 4, 5. And between carbon 2 and 3 is a double bond. At carbon 3, there's a methyl. At carbon 4, there's a methyl. Draw that in a three-dimensional way. Well, again, start with the origin here. What I mean by that is double bond CC, and I know it's between carbon 2 and carbon 3. Carbon 2 and carbon 3, so that's what I've just drawn, carbon 2 to carbon 3. Now what? Around the double bond, we have a carbon, here's one coming off, alrighty, and another carbon coming off. Notice here how I'm looking to see what's coming off of the double bond carbon. Well, in one direction, I have the CH3 group. I drew that here. And in the other direction, I have this, what I'd call an isopropyl group, C, but we could, if we wanted to, just do CH3 taken twice. Or you could kind of go C, and then you'd have, kind of coming here, you'd have branching this way. That's kind of showing the structural of isopropyl. Either way would be fine. And then kind of coming back here, if this over here now is, oops, I need that to be cis. Oh, that's straight chain. If it's cis, I have to come straight down here, CH3, and this, of course, would be the other hydrogen. Carbon 1, 2, 3, 4, 5. Kind of think of that here. This would be carbon 3, 4, 5. Here's 4 and 3. We have 3,4-dimethyl 2-pentene. And the cis is showing us that these guys, the main branch are indeed on the same direction of that double bond. The substituent group is pointing up. That's fine. But the main branch around that double-to-double bond are pointing in the same direction. So incorrectly drawn, C double bond C, we would not want that isopropyl group coming up and the other one coming down. So this represents the trans isomer because the main branch, 1, 2, 3, 4, 5. The main branch are on opposite sides of the double bond. The main carbon chain are on opposite sides, trans. If the main carbon chain are on the same side of the double bond, cis. Let's try some and just keep working. Here's one on page 357. I have this with CH3, CH2, CH2, and I'm brought down, C double bond C, CH2, CH3. These, of course, are hydrogens. Considering the cis-trans geometry, name that compound. Well, again, I start numbering from the side that gives the lowest number to the bonds, the carbons involved in the double bond. So not up high here, because 1, 2, 3, 4 versus 1, 2, 3. So here's my carbon 1, 2, 3, carbon 4, 5, 6, 7. From the main carbon chain, the carbon chain are on opposite sides of the double bond, which represents the geometry known as trans. The double bond begins at carbon number 3, and there is a total of 7 in that chain. Trans 3-heptene. Try another. CH3, CH2, CH2, C, double bond C, CH2, CH3. Keep drawing with me. Alrighty. Let's name that, including the geometry. Highest priority, the longest carbon chain that contains the double bond, where the double bond gets the lowest number possible. Carbon 1, 2, 3, 4, 5, 6, 7. At carbon number 3, I have a double bond in a 7-carbon chain, 3-heptene. And at carbon number 4, we can see this substituent group, a methyl. At carbon number 4, we have a methyl group. And then what about the geometry? So notice here the double bond. We want to consider the main branch in relationship to the double bond. Since they are on the same side of the double bond, the geometry here is cis. Cis, 4-methyl, 3-heptene. Let's keep drawing. We're doing well. I'll try another with you. Best you can, model that particular picture, and we're going to name it. The lowest carbon chain, the longest carbon chain that contains the double bond, numbering from the side that gives it the lowest number. So 1, 2, 3, 4, not that direction. I could go 4. I could either go up or down, doesn't matter. I'll call that 5. 1, 2, 3, 4, 5. Between carbon 2 and 3 of a 5-carbon chain, there's a double bond. So I know I'm starting with 2-pentene. What else do we have going on? At carbon 3, I have a methyl, and at carbon 4, I have a methyl group. So far, I could label this as 3, 4, dimethyl. And the geometry needs to be considered. Notice that here is the carbon chain with a double branch. In the double branch, part of the chain is pointing up, and the other part of the longest chain is pointing down. From the carbon chain that is the parent branch, not the substituent group, but the parent branch, this represents the molecular geometry called trans. Trans 3,4 dimethyl 2-pentene. What the heck? Let's try one more together. Again, draw your best with me. There, that's not so bad. Name that. Well, all right, let's count how many carbons, knowing that the priority comes from the lowest number first. So the longest chain with the double bond, giving the double bond the lowest number. 1, 2, 3. 1, 2, 3, 4. So I'm going to count from right to left. 1, 2, 3, 4, 5, 6, 5, 6, 7. All right, carbon number 3, we have a 7-branched double bond. 3-heptene is my root word. Now what else is going on? At carbon number 4, I have an ethyl group. So I can include that as writing 4-ethyl, ETHYL. And now the molecular geometry. Here's the double bond. The parent branch, one side goes up, and the other side is on the same side as the double bond. Same side gets the molecular geometry of cis. Cis, 4-ethyl, 3-heptene. Let's consider cycloalkenes. Those alkenes that are in a cyclic ring. To name the cycloalkenes, we number the carbon atoms of the ring that contains the double bond, assigning it a number 1 and a number 2, in the direction that gives the lowest number to the substituent group encountered first. Let's model what that would mean. Getting a pen ready. Here is a double bond in a 5-membered ring that has a substituent group. A 5-member cycloalkene would be called cyclopentene. Now, if there were no substituent group, its name would simply be cyclopentene. However, there is a branch coming off of the cyclic structure, and it needs to be named. By awarding this position number 1, 2, and 3, notice that the double bond must be given priority with the carbon number 1. At the 3rd position, there is a methyl group. Not 1, 2, 3, 4, 5. Not 5-methyl cyclopentene. Sorry, I said the word protein there. Here is a 6-membered ring with 2 substituent branches, but the double bond gets the priority when numbering the carbon. Not the alphabetical order of the substituent groups, but the double bond. At carbon number 1, that's where we encounter our first substituent group, and it happens to be methyl. At carbon number 4, we have a second substituent group called ethyl. The numbering gets priority with the double bond, but they are named in alphabetical order. Properly named 4-ethyl, 1-methyl cyclohexene. Shall we try some of these? Let's draw a 6-membered ring. We'll place a double bond and 2 methyl groups coming off the top. That looks like a fun structure. Name that. The numbering of the carbon must contain the double bond heading towards the lowest number of the substituent group. So carbon 1, 2, 3, 4, 5, 6. It's a 6-membered ring. Now, at carbon 3, we have 2 methyl groups. 3, 3, dimethyl. Now, this is important. We just write cyclohexene. We do not write that as 1-cyclohexene, because we understand the IUPAC rules say we already know that the number assigned to the carbon contained the double bond, leading to the lowest number of the substituent group. This already indicates where the substituent groups are in relation to the double bond. We do not need to number the position of the double bond. We do in straight chains, but not necessary in the cyclic structure. Try another. Let's draw a 5-membered ring. 1, 2, 3, 4, 5. I'll have a couple of methyls and a double bond there. That's a 5-membered ring with a double bond and a methyl group. Now notice 5 members. If I start here or here, we're going to end up with the same name. 1, 2. But the bond must be included. So here we have cyclopentene. Excuse me. And at carbon 1 and 2, and again, if we numbered the opposite direction, we'd come up with the same name. 1, 2, dimethyl cyclopentene. One more for the cyclic structures. Let's draw a 6-membered ring. Let's have a double bond. I'll just put it here for ease. We'll have a methyl group coming off of the side with the double bond. And let's see, 1, 2, 3, 4, the other bond right here. Let's draw that. Right away, I drew a 6-membered ring, so I knew my root word, cyclohexene. The numbering must contain the double bond. So let's decide, would it make sense 1, 2, 3, 4, 5, 6? Or would it make better sense to go 1, 2, 3, 4, 5, 6? Which one gives the lowest, the number to the lowest substituent group first? Well, originating as I drew in blue gives the methyl group the number 1. Drawing as I did in red, the methyl group is assigned the number 2. So the blue wins. We have at position, I'm not naming it, but I'm just kind of getting my positions ready. I have a 1-methyl and a 4 isopropyl. And again, here's 1, 2, 3 carbons in a branched geometry. That's isopropyl. But now, how do I name those? Well, I name them alphabetically. So in order of the alphabet, 4 isopropyl, 1 methyl cyclohexane. And try one more just to get our confidence. Oh, let's try a 6-membered ring. I'm getting good at drawing those. I'll try this direction. 6-membered ring. That looks great. I'll draw a double bond and then a structure like this. Name that. Well, we want to number the bond. Should I go 1, 2, 3, 4? Or should I go 1, 2, 3, 4? Well, in this case, interesting enough, we ended with the branch at number 4, but keep in mind the rule says I have to number the branch that contains the double bond. So what I drew in red was completely wrong because I didn't even start number 1 with the double bond. So let's erase that. Is there any other pattern to draw? What if this were 1, 2, 3, 4, 5? Well, clearly what I drew first is a better arrangement in terms of lower numbers. So I think that's it. I have to redraw. Just trying to get my bearings straight. Let me redraw. Sorry, yours is still on the paper. There's my 6 carbons, kind of giving it a quick draw. But what we did decide, based on the lowest possible number, 1, 2, 3, 4, we're going to number in this fashion. Is 1, 2, 3, 4, 5 clearly has this substituent branch at a higher number. Okay, so here's what we know. We have cyclo hexene. And at carbon number 4, we have a branch. Let's count the number of carbons. 1, 2, 3, 4. So it's a butyl. You see how on this carbon, there is 1, 2, 3 carbons attached to this? That's what we call tert, standing for tertiary, which sometimes you see written as that component of 3 degrees. 1, 2, 3, tert butyl. Oops. Oh, you're probably getting tired right along with me. T-butyl. 4, tertiary butyl cyclohexene. Tert butyl gives us that tertiary for the 3 carbons in this substituent group. We'll end with another thought on cycloalkenes. Those that contain more than 1 double bond, or alkynes that contain more than 1 double bond, are known as dienes, or trienes, or so forth. Prefix poly means many double bonds. Naming them is pretty straightforward. We're just going to include the prefix di to indicate that there's more than 1 double bond. In this structure, at carbon 1 and at carbon 4 of a 5-carbon chain, between carbon 1 and carbon 2 is a double bond, and between carbon 4 and carbon 5 is a second double bond. 1, 4 pentadiene, a total of 2 bonds between carbon 1 and 2 and between carbon 4 and 5. 2-methyl 1,3-butadiene. Between carbon 1 and 2 is a double bond, and between carbon 3 and 4 is a double bond of a 4-membered chain, butadiene. And coming off of carbon 2 is a methyl group. Carbon 1, 2, 3, 4, 1, 3 butadiene, and at carbon 2 is a methyl. If we had numbered from the right to the left, we would not have given our substituent group the lowest possible number. So this direction got priority. And here's the cyclic structure, a 5-membered ring, so we see that it's pentadiene. Now we're telling you the origin of those carbons. Between carbon 1, 2, there's a double bond, and between carbon 3 and 4, there's a double bond. 1,3 cyclopentadiene. 1,3 cyclopentadiene. What if we saw a structure CH3, CH, double bond CH, CH, double bond, CH2, CH3. Name that. Well, we can clearly see there's 2 double bonds. All right, so here's a functional group, and here's that other. So it's going to be a diene. How many are on a carbon chain? 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. What's our best numbering system? Between carbon 2 and 3, or between carbon 2 and 3? Aren't they created equal? So it didn't matter right or left. We have a 6-membered ring, and there are 2 double bonds. So I know it's going to be di, hear that for the 2, and then we'll end in ene. The root word is hex, hexadiene. Hexadiene, 6 carbons, and then we see that the double bonds in either direction were between carbons 2 and 4, between carbon 2 and 3, and between carbon 4 and 5. Are there any branches to name? No. 2, 3, 4, 6,2,4 hexadiene. I'll stop my lesson here. When you're ready, the next part of the lesson is physical properties and so forth, but you really should practice this first half before you start the next set of lessons.